Hello and welcome. So today we will learn more all about the divergence theorem. This is an additional method for calculating the surface integral for a closed surface S. By this, we mean that we have some solid region in space, and its boundary will be our surface. Recall that the surface integral for this will be expressed as the surface integral over S of f dot n ds, where f is some vector field permeating space, and n is the normal vector of the surface. The divergence theorem, also called Gauss's theorem, states that this surface integral is equal to the triple integral over the solid region of the divergence of f dv. Here, dv is our differential volume, which in Cartesian xyz coordinates will simply be dx, dy, dz. Let's take a look at an example to see how to apply this theorem. Consider the surface of this triangular prism, which occupies x from 0 to 1 and y from 0 to 2. It has a flat base in the xy plane, and the top surface is given by the plane z equals 1 minus x. Now let's say there's a vector field in this space, which is given by f equals xy, yz, zx. If we wanted to calculate the surface integral of this field over the surface S without using the theorem, we would have to split each of the 5 flat surfaces of the prism of their own surface integrals and calculate each individually. Luckily, the divergence theorem reduces our work to one triple integral over the region of the prism. The divergence theorem states that the surface integral will be equal to the triple integral of the divergence of f over the region. So first, let's find the divergence of f. Recall that the divergence of a vector field is del dot f, where del equals ddx, ddy, ddz. So for this case, the divergence will be del dot f equals y plus z plus x. Now we have the divergence, but before integration, we must get our bounds sorted out. We get these from the region of our prism. One simple way to express these bounds is integrating z first, letting it run from 0 to 1 minus x. Now we don't have any more complicated bounds, so we can integrate y from 0 to 2 and x from 0 to 1. So our integral ends up from being the integral from 0 to 1, from 0 to 2, the integral from 0 to 1 minus x of y plus z plus x dz, dy, dx. Integrating z first, we get yz plus z squared over 2 plus xz, where z is evaluated from 0 to 1 minus x. Factoring out a z and evaluating, we get 1 minus x, y plus 1 minus x over 2 plus x, or simplifying the x terms, we get 1 minus x, y plus x over 2 plus 1 half. Next, we must integrate with respect to y, which gives us 1 minus x, y squared over 2 plus xy over 2 plus y over 2, where y is evaluated from 0 to 2. Evaluating this, we get 1 minus x times 2 plus x plus 1, or just 1 minus x times x plus 3. Now, if we multiply this out, we get the integral of x plus 3 minus x squared minus 3x dx. Simplifying gives us 3 minus 2x minus x squared. Integrating, we get 3x minus x squared minus x cubed over 3, where x runs from 0 to 1. And finally, evaluating gives us 3 minus 1 minus 1/3, simplifying to 5/3. This is the value of our surface integral, which we use the divergence theorem to calculate. And now, let's try with another example. So let's start with a given of the vector field is equal to x squared, 0, and xz. Recall that the divergence of f is equal to del dot the vector field f. Therefore, del dot f is equal to d over dx times x squared plus d over dy times 0 plus d over dz times xz. Deriving will give us 2x plus 0 plus x. Therefore, our del dot f is equal to 3x. Then applying our formula, which is the divergence theorem. So let's start with integrating with respect to z. Starting with 3x, integrating gives us 3xz running from 0 to x squared. Evaluating this will give us the answer 3x times x squared, leaving us with 3x cubed. Next is we are going to integrate it with respect to y. So let's start with the previous integrated value of 3x cubed. We get 3x cubed y, where y is evaluated from -2 to 2. Evaluating this gives us 3x cubed times 2 minus -2 dx. And we get 12x cubed dx. And lastly is we are going to integrate this with respect to x. So starting from the 12x cubed dx, which we have derived from our previous integration of y and z, we get the 12 times x to the 4th over 4 running from 0 to 2. Evaluating gives us 12 times 2 to the 4th over 4, and finally giving us the answer of 48. So this is our value of the surface integral using the divergence theorem.